Welcome everybody to this fourth session, technical session about theoretical and conceptual issues of AGI systems. We will have 5 talks. We will do it as in the 3 predecessor sessions. So speakers will get around, I don't know, 12 minutes plus 3 minutes of questions. And we try to stick to the time schedule. At the beginning, Tarek Besold will talk about a note on tractability and artificial intelligence, and I will not interrupt him because he will give his second presentation by changing slides. The slide set about human-level artificial intelligence must be a science. So,
could you give me a quick heads up, like after 10 minutes?
Okay.
Yeah. Time-wise? Good. Okay. As I already said yesterday, this is basically the continuation of the second part of yesterday's presentation. Whilst yesterday the part on HTTP was rather the technicalities, here you're now getting the ideology or the propaganda behind it. This is still joint work with Robert Robert from the University of Toronto. Okay, so let's get to it. Tractability and AI. That's kind of a topic that frequently comes up in one way or another, as we already saw during the workshop day. And we basically spent a bit of time on thinking about it and trying to come up with our own story or our own account on how both could be recoupled. Before directly getting there, I will have to give a bit of a background. So if you have a look at the history of AI and the philosophy of AI or the philosophy of mind, basically you figure that 2 famous ideas are at least at the heart of most of what we consider strong AI. On the one hand, you have the computer metaphor of the mind, so the idea of a computational theory of mind, how it was originally propagated by cognitive science. And on the other hand, you have the Church-Turing thesis, so the hypothesis that every kind of algorithmic procedure can basically be formalized in terms of a Turing machine. If you take the computer metaphor of the mind and you think about it, you figure that this metaphor basically bridges the gap between humans and computers. So the human mind and brain or brain can be seen as information processing system, and reasoning and thinking would then correspond to computation as formal symbol manipulation. Now, adding the Church-Turing thesis, the thesis gives an account of the nature and the limitations of the computational power of such a system. So if you say, okay, my mind corresponds to some form of Turing machine, you have a rather crisp idea of what is doable and what would not be doable, given that you buy into it. These observations basically also had a severe impact on cognitive science and precisely cognitive psychology. So what is cognitive psychology doing? Basically, these guys are trying to explain human cognitive capacities in models which use computational level theories. So some of you might have heard about David Marr and his 3-level hierarchy, where you have computational level, algorithmic level, and implementation level. A computational level theory is the most general or most abstract idea of the 3, and what a computational level theory basically is a precise characterization of hypothesized inputs and outputs of the respective cognitive capacity at hand, together with a functional mapping between inputs and outputs. Now, if you have a look at cognitive psychology, you basically have one severe problem. Normally, the computational level theory is underspecified by the data you get. So you have inputs, you have outputs, but the functional mapping between the 2 is hardly ever unambiguous. You can come up with different functional mappings for sets of inputs and outputs. Now, researchers in cognitive psychology already in the 80s then proposed, well, maybe we can use complexity theory for at least restricting the space of options. And the most salient concept for doing so clearly is NP completeness. So this was coined into the P-cognition thesis, or the polynomial cognition thesis, which proclaims that human cognitive capacities are hypothesized to be of the polynomial time computable type. There are now different interpretations to how to read this statement, where what Robert and I actually see in it can be paraphrased as humans can comfortably solve non-trivial instances of a problem where the exact size depends on the problem at hand. So It's just that you have a polynomially computable problem, and as long as the instance stays kind of comfortable and kind of bounded in size, we can solve it. But now, the question which was discussed by some theoretical cognitive scientists over the last decade mostly is, maybe polynomial time computable is still too restrictive. So is it really that polynomial time computable is the meaning of efficient? It clearly shows that humans are able to solve problems which would be hard in general. But if you restrict certain parameters of the problem, they become feasibly solvable. And this now, the idea itself was formalized in a field called parameterized complexity theory. So if you remember my last talk, I already introduced some of the notions. And precisely there it was captured in what's called fixed parameter tractability. So the idea is, given that I keep certain parameters of a problem fixed, problems which in general might be non-tractable could become tractable. This, of course, now can be translated in a thesis similar to the P-cognition thesis before, where I say, okay, FPT cognition thesis, human cognitive capacities are conjectured to be fixed parameter tractable for one or more input parameters which are small in practice. So the computational level theory has to be an FPT. This thesis, coupled with some of the analyses I showed you yesterday, can now be used for reintroducing the idea of tractability to AI. Clearly, some of you guys will now say, wait a second, already people way back did this, with some of the most prominent ones also being Gerhard Brefka. Yes, but they only did it for polynomial tractability, which I think is overly restrictive. So we take the FPT version and we convert it into, well, an FPT AGI thesis. So what we actually demand, claim, hypothesize, phrase it however you want, is that models of cognitive capacities in AI and computational cognitive systems should be fixed parameter tractable for one or more input parameters which are small in practice. So they should be an FPT in order to have a realistic chance of really being scalable into a general cognitive architecture that comes up with high-level intelligence and a broad notion of intelligence. Giving you a worked example, we do a bit of history. So if you have a look back in the history of AI, you will see that originally most of what AI did was based on classical logic. It pretty quickly showed that classical logic had one severe drawback. Precisely, you couldn't capture cognitive phenomena because, well, in cognition you have defeasible reasoning, you have non-sharp boundaries, you have things which might not precisely be binary in their truth values. Okay, so for doing this, people introduced non-standard logics, non-monotonic logics, with one severe drawback. At least I would hardly be aware of a powerful non-monotonic logic reasoning formalism which is not intractable. So as soon as you go non-monotonic, normally tractability goes out of the window. We're talking NP hard or worse. But now if we also assume that P is not equal NP, NP hardness yet again breaks the tractability rule. So there probably is no efficient algorithm which exactly computes processes of reasoning exactly for any set of input parameters. This led to a progressing abandonment of the logical approach to modeling cognitive capacities, and people searched for a new way. At least in the cognitive modeling camp, quite some people are now doing Bayesian probabilistic models. And they say that, okay, Bayesian probability might do what logic failed at doing. Unfortunately, if you have a look at what Bayesian probability does, at least in the most probable explanation way, it's still NP hard, and it's even worse, as NPE Bayesianism, most probable explanation Bayesianism, is even intractable under approximation. So Johann Quisthout and some of the guys already 5-6 years back showed that if you want to have an arbitrary approximation of NPE reasoning, you are far beyond tractability. Still, as it might have been the case in the non-monotonic logics case, we would say that abandoning Bayesian reasoning merely for the intractability would be premature. There are different proposals for how tractability could be restored. One of them being the naive one, well, maybe we just have to restrict the input domains. This is probably a good idea, problem just being no one really figured how to do it in a meaningful and helpful way. What we now would advocate is a bit more pragmatic and less ambitious. We'll just take the tractable AGI thesis and use it as a principle for deciding whether a particular Bayesian style model is worth investing further effort or not. So take your Bayesian style model you got at hand, and if you can show that it's fixed parameter tractable for some set of parameters kappa, where kappa in reality corresponds to some normally narrow set of things or elements, then I think you're still on the safe side. So just make sure that your input parameters, the relevant ones, stay small in reality. Maybe we are just never facing the big problems, so maybe intractability just never hits us. And carry this idea over to the AGI and cognitive models. Also, there is a beautiful non-trivial corollary to the FPT part. Namely, any instance of an FPT problem can be reduced to what's known as a problem kernel. So, kernelization. Take some parameterized problem, and a kernelization of P is an algorithm which takes an instance of the problem with parameter kappa and maps it in polynomial time to an instance y such that x is in the original problem if and only if y is in the original problem, and the size of y is bounded by a function of kappa, where the function has to be computable. What you actually do is you reduce the problem size to an equivalent problem. So it shows that a problem P is in FPT if and only if it is kernelizable. As soon as I have a problem in FPT, I can kernelize it to a smaller instance which is solution equivalent. Two important observations from this. So the first one is any positive FPT result implies the existence of this downward reduction. And if you now still assume that W1 is not equal fixed parameter time tractable, so if you assume the analog scheme to n not equal np, p not equal np, then you as well can say that any negative result implies that there is no such downward reduction. This now, again, beautifully binds back to cognitive science, and that this correspondence between problem instances and a reduction is very often reflected in what you find in cognitive psychology and kind of in spirit related to what you find in the heuristics and biases program. So cognitive psychologists frequently encounter the phenomenon that people in problem solving actually do not solve the original problem, but they have some way of reducing it to a simpler equivalent problem, and then they bring back the solution from the simpler one. Whilst what I already mentioned before with the heuristics and biases, okay, you can give different readings to what a heuristics is. But some people just say you don't solve the original problem, but you solve the problem by simplifying it. And here, okay, this basically is what a kernelization does. It makes the problem smaller. I know that is only one possible reading of simplification, but it is a reading. So what we would say here is that kernelization and kernelizability can provide inspirations and first hints at hypothesizing some specialized cognitive structure which is capable of computing reduced instances of problems, which clearly is relevant for the cognitive side, but clearly could as well be relevant for us. So if we would figure how people do this simplification, this clearly could directly be applied in an AGI system. How am I doing time-wise?
You should slowly.
I should slowly? Okay.
Come to an end.
Good. This would be the first talk. If you're interested in these tractability and approximability issues, of course you're happily invited to talk to me, to contact me or my co-author, or if by any chance you should be around Oxford in late September, there is a expanded version of the overall thought in a talk called When Thinking Never Comes to a Halt, Tractability, Colonelization and Approximability in AI at a beautiful event which is called Philosophy and Theory of AI. And as I think I'm giving the next talk as well, I will just swap 1 minute from there to this talk, because there's a second reading to heuristics. Either you say you simplify the problem, or you say, well, maybe you don't really solve the problem, but you just approximate it. So maybe you don't want to have the precise solution, but what you want is you want to be good enough for some notion of good enough. There as well is a formal theory beautifully covering this, which is approximation theory. So the notion we consider most promising here is called constant factor approximation, which tells you that actually you want to have an approximation bounded by a meaningfully chosen constant factor. So you don't want to solve it perfect with approximation ratio 1, but you want to solve it with 1 plus epsilon, where now, depending on your problem, you would pick the epsilon. Maybe you don't want to have the classical example Gigerenzer uses is actually marriage and partner selection. So maybe you don't want to have the perfect partner, but you want to have a partner who is, say, 95% perfect and you're still happy. So you can also capture this in formal notions. And beautifully enough, if you now take fixed parameter tractability, and the constant factor approximability, there is one concept which generalizes both and is implied by both, which is called fixed parameter approximability. Saying that, okay, if I have a problem where I keep certain parameters fixed, I can approximate it up to a certain ratio. And yeah, if you think that our fixed parameter tractability thesis is too strict, maybe you want to have a shot at the way more general fixed parameter approximability understanding of the entire thing. More details, Oxford, late September. Okay, thanks. That was the first one. Any questions, comments urgently here? Yeah.
Do you think that when you fix one parameter, you can use some techniques of meta computations?
Yeah.
So these are related things,
Yeah.
yes?
The entire idea of metacognition or metacomputation goes along the same lines, in my opinion. So they are not directly technically equivalent as far as I saw, but at least the people I'm normally coming along best with are the people doing metacognition, because they as well say, okay, maybe you just extract certain parameters from the original problem, move them to the higher level, solve them, and then can plug them in again. So yeah, I'm perfectly fine with that.
Well, but you're talking about metacognition, but I'm talking about particular techniques of partial evaluation and so on.
Yeah, okay. I have to admit we never really looked into that, how we would plug it in. But intuitively I would say, yeah, you got a point.
Okay, thanks.
Just a quick comment you said about the last session.
Yeah.
About heuristic algorithms where you have good enough with this good enough defined. But for heuristics it's different, because in heuristics you don't have a specific number. I mean, if you have approximation algorithm, then you guarantee the approximability within a certain bound. But if you have heuristics, in general, you don't have this bound. What do you see? You see it in this regard?
Well, the question is what you read into that boundary. So if you take the psychologically motivated side, there clearly is a satisficing boundary. So Herbert Simon proclaimed that notion of satisficing, where you say, okay, I don't want to be perfect, I don't want to be good enough. The problem about this, I have to admit, is that probably the boundary is problem specific. So you can't give a general boundary and say something like, whenever I want to be 10% close. But still, going by problem, you can have the boundary.
But what about algorithmic wise? I mean, you might follow some techniques for heuristics that guarantee some good solution, but does not guarantee some boundary.
Yeah, okay.
you example chess. I mean, chess
Yeah.
heuristics, right? I
Yeah.
mean, it works fine, right?
Yeah.
But you can't have an epsilon.
Well, okay, don't get my message wrong. The overall spirit is not that it necessarily and always, in order to do the job, has to be tractable. The overall spirit is more like, if you want to make sure that it scales up, as long as you stay on the tractable side, you're on the safe side. And of course, there are as well people who would just argue that maybe human cognition solves the issue by itself. So maybe we are super Turing computers or what have you. I'm clearly not going down that road, but I can't refute that argument either, just due to lack of evidence. But I would still say, okay, if you want to play it safe and if you want to play it, in my opinion, reasonable, try to stay on the tractable side. Yeah.
I would propose we
Yeah, we switch talks.
already a little bit late.
Okay. Good. Well, this one actually